In section 4.6, we're going to introduce the concept of rank and nullity, talking about an important theorem, the rank-nullity theorem, and then finally conclude our invertible matrix theorem with a few extra equivalent conditions. So first, let's talk about the row space, which is going to be similar to the column space of A, except talking about the rows. The set of all linear combinations of the row vectors of a matrix A is called the row space of A and is denoted ROW of A, row of A. So let's look at an example. This matrix A is a 3x4 matrix, and if we look at the rows, we're going to be writing them as 1x4 vectors, horizontal vectors. We have the first row, -1, 2, 3, 6, gives us our first row vector, -1, 2, 3, 6. And same for row 2 and row 3. And what the row space is going to be is the span of all three of those vectors, noting that is a subspace of R4. Now naturally, we're going to express those vectors horizontally when we're talking about the row space. We can also talk about them as column vectors, and that's the idea that we can instead look at the transpose of the matrix. And the transpose of the matrix A is switching all of the rows and columns. This would be -1, 2, 3, 6. That is the first vector in the row space. 2, -5, -6, -12. And then 1, -3, -3, -6. So instead of talking about the row space of A, we could equivalently talk about the column space of A transpose, noting in this example that the span of those three vectors written in a vertical form give us the column space of A transpose. Noting that we could have written this as, if we think about the row vectors from the beginning, the span of our row vector 1 transpose, the second row vector transpose, and the third row vector transpose. That would make them column vectors. All right. One important use for the row space is that we can talk about row operations to reduce matrix A to matrix B. And when we do the row operations, what we're really doing is taking linear combinations of the rows of A to come up with the rows of B. All of our elementary row operations, let's write those down. Our elementary row ops, we have that we can take a constant multiple times a row. We can swap one row with another, and we can add a multiple of one row to another and replace it with the new row. And these are just going to be linear combinations, these new rows that we get, of Ri and Rj. The only one that's kind of weird, doesn't immediately show it's a linear combination, is the second one. But all that's saying is that you can add things. It doesn't matter what order you add them in. You could add the first row plus the second row, or the second row plus the first row. It's the same idea. The order that you add them in is not an issue if we're talking about a linear combination. And since we're talking about the row space, we're talking about the rows as vectors. And now we're saying that those the span is going to be the same for A and B. And what that really means is that if you have two matrices A and B, and they are similar, that means that you can get from one to the other in terms of elementary row operations, then the row space of A has to be equal to the row space of B. And this theorem says that explicitly. If two matrices A and B are row equivalent, then their row spaces are the same. If B is an echelon form or reduced echelon form, the non-zero rows of B form a basis for the row space of A as well as B. So to make this clear, we're going to do an example on the next page, but if we want to find a basis for the row space of A, what we're going to do is we are going to find the row reduced echelon form of A, and we're going to call that B, and then we're going to use the non-zero rows of B to form the basis. And a word of warning, this is not the corresponding rows in A. And the reason for that is because a row of zeros could potentially mix up the linear dependence relation. And because of that second row operation, or that second elementary row operation, we may be changing the order of the rows, and they may not correspond to the original rows in the matrix A. And we'll see that in the next example. So this is how we're going to find the basis for the row space of A. It's similar to how we found the basis for the column space of A, except one notable difference is we are going to use the non-zero rows of the reduced echelon form. So here's an example. We have two matrices below, A and B. They're row equivalent, and we know that this is going to be the row reduced echelon form of the matrix A. We're going to find a basis for the row space, the column space, and the null space of A. And if we can do that, we can quickly state the dimension of each of those. So if we find the row reduced echelon form, that's going to give us most of the information that we need to find these bases. The basis for the row space is going to be the non-zero rows of B. So there are three possible rows, but we are not going to include that third row because it is a row of zeros. So our basis is going to be the matrix or the vector 1, 0, -3, -6, and 0, 1, 0, 0. And you could write this as a matrix, or you could write this as a vector with parentheses as well and commas. It makes no difference. It just depends on what context you're thinking about them in. So look at the non-zero rows of B. Not those of A. And again, the reason for that is because in this matrix B, this row reduced echelon form, the rows, all of them, form a linear dependent set. That row of zeros is a linear dependent set. And the rows of A will be a linearly dependent set. So it might be that one row is a constant multiple of another. But we don't know which rows they are in the original matrix A because we might have swapped the rows as we've done the row operations. So that's why it's important to use the rows of B instead of those of A, the corresponding ones. Whereas for the column space, we're going to see in a second, we want to use the original columns of A. Because there are two vectors in the row space for the basis, the dimension of the row space is A. Now for the column space of A, we're going to look at the pivots of the row reduced echelon form, and these correspond to the pivot columns of the original matrix, and we do want to use the original matrix A here, and those columns form a basis, -1, 2, 1, and 2, -5, -3, for the column space of A. And in this case, we have two vectors in the basis, so the dimension of the column space will be 2. And again, these vectors are the pivot columns of the original matrix A. And then when we look at the null space of A, that's the different one where we have to look at the homogeneous equation AX equals 0. So first we solve that homogeneous system, noting that we end up with the row reduced echelon form over here, augmented with the 0 matrix. We can see that most of our information comes from that row reduced echelon form. And when we write the corresponding solution to that system, we have our equations here, x1 minus 3x3 minus 6x4 equals 0 and negative x2 equals 0. I should note this should be a positive 1 for the row reduced echelon form, just multiplying that row by a positive 1. And when we do that, we get these equations. X1 is 3x3 plus 6x4, x2 is 0, and then x3 and x4 are free. And since we can write the system as a linear combination of those free variables, we have 3x3 plus 6x4, 0, x3, and x4. We can write this as a linear combination of those vectors, and those vectors form a basis for the null space of A. Right, and these are the vectors that correspond to the free variables in our matrix. And in this case, the dimension of the null space is going to be 2. So, a bit of review here. We have the dimension of the column space of A is equal to the number of pivots of A, and that's the same thing as the number of non-zero rows in B. Note that B here is the row reduced echelon form of A, and that's going to be the dimension of the row space. So the dimension of the column space is equal to the dimension of the row space always. And likewise, the dimension of the null space is going to be the number of free variables, and that's going to be the number of non-pivot columns of A. So now we can introduce our important concept of rank. The rank of A, denoted rank of A, is the dimension of the column space of A. So rank of A is the dimension of column space of A. You can also think about rank of A as the number of pivot columns of A. That's an idea that we brought in the first section of this course. We can also think about it as the dimension of the row space of A. That is the number of non-zero rows in the row reduced echelon form. Now we're also going to talk about the nullity of A, denoted nullity of A, which is the dimension of the null space of A. So nullity of A is dimension of the null space of A. That's going to be the number of free variables of A, or the number of non-pivot columns of A. So when we're looking at the relationship between the rank and the nullity, we get this very important relationship that if you add the rank plus the nullity of A, you get equal to n, which is the number of variables in our system of equations, or the number of columns. So we can see this rank of A is the number of pivot columns of A. The nullity of A is the number of non-pivot columns of A. And if we add all the pivots plus all the non-pivots, we get all the columns of A. And this brings us into our rank theorem, or rank nullity theorem. The dimensions of the column space and the row space of an n by n matrix are equal. We talked about that in the previous page. And this common dimension, known as the rank of A, also equals the number of pivot positions in A, and satisfies this important equation: the rank of A plus the nullity of A is equal to n. And then furthermore, since the row of A, the row space of A is equal to the column space of A transpose, you talked about that on the first page, that if we just transform all the columns into rows and rows into columns, we can think about A transpose instead. We now know that the rank of A is equal to the rank of A transpose. Another way to think about this important equation, rank of A plus nullity of A, we can say that rank of A is the same thing as the number of basic variables the nullity of A is the number of free variables, and this is going to be equal to n, which is just the number of variables that we have, or the number of columns. So instead of thinking about this in terms of the number of columns, you can think about this as the number of variables instead. And we learned in the first section of this course that columns represent variables in our matrix. There's also a lot of a lot of stuff going on here with the transpose of the matrix. We're going to see at the end of this section, and we can talk a lot about that. But there's something important about the transpose related to just the original matrix, and that's the idea of the row space and the column space both being important. So let's look at another example. Suppose that we have a 5 by 8 matrix A, and it has rank 5. We're going to find the nullity of A, the dimension of the row space of A, and the rank of A transpose. And then we're going to ask the question, is the column space of A R5? So, to do this, we're going to look at our rank nullity theorem, this equation that we get, that the rank of A should be plus the nullity of A is equal to n. And since the rank of A is equal to 5 and n is equal to 8, we're going to solve this equation. 5 plus the nullity of A equals 8. So the nullity of A is equal to 3. Another way that we could say this is that the rank of A tells us that there are 5 pivot columns, and the nullity of A tells us the number of free variables. And if we know there are 5 pivot columns, there has to be 3 free variables in our system, or in our matrix, not necessarily a system. Then we have the dimension of the row space of A is another way that we can define the rank. It's equal to the dimension of the column space. We are given that that is equal to 5. And the rank of A transpose is equal to the rank of A, so the rank of A transpose is also 5. So since the rank of A is equal to the number of pivots in A, and that's 5, there's a pivot in every row, and we have a 5 by 8 matrix. So we have 5 equations, 8 unknowns. There has to be 5 pivots, which means that there is a pivot in every row. Not in every column, but in every row. Therefore, the columns of A have to span all of R5. And hence, the column space of A is equal to R5. If there was a row of zeros, or there wasn't a pivot in every row, then the column space of A would not span all of R5. That means that we would have a linear dependent set of rows. We wouldn't be able to span all of R5 there. Note that in this little example I have with the 5 by 8 matrix, we have 3 free variables based on the position of those pivot columns that I randomly made up there, but that would work out. This also means that if we have a system of equations, this system is consistent, but there will be infinitely many solutions. And we're going to talk about bringing it back to that idea at the end of this section. So let's look at another example. Let's say we have a 9 by 12 matrix A, and we're going to find the smallest possible value of the nullity of A. That is the dimension of the null space. So again, we're going to use our rank nullity theorem, that the rank plus the nullity is equal to n, in this case 12. And then solving for the nullity, we have nullity of A is equal to 12 minus the rank of A. So if I want to find the smallest value of the nullity, I have to find the largest possible value of the rank. And in that case, this is going to be 9. And to see this, we can look at a 9 by 12 matrix. So this is a 9 by 12 matrix. And we know that the rank of A is equal to the dimension of the column space of A. It's also equal to the dimension of the row space of A. And we think about the column space of A, there are 12 vectors total that we're talking about, 12 different columns. So the dimension has to be at least less than or equal to 12. But then if we think about the row space of A, we have 9 rows that we could possibly have. Now, it might be less than this, but we know that it has to be at most 9. So therefore, the biggest value the rank can be is 9. Even though if we think about it as the column space, it could be more, but we can't have more than 9 pivots that we have there. Or think about just the row space. This means that the smallest possible value of the null space is 3. That means that there are at least 3 free variables. So now let's talk about just a matrix A. We're going to talk about the row space and the null space and the column space, and then also a new space we're going to talk about the null space of A transpose. So we have our matrix A here, 1, 0, 1, 2, 0, 2, and let's also look at the row-reduced echelon form of A. And that's going to be very easy. We just do -2 row 1 plus row 2, and that will give us a row of zeros in the second column and 1, 0, 1 on top. And since we're going to use the row-reduced echelon form to find the bases for these subspaces, it's good to find that. So we can find this on our own, but the basis for the null space of A, it's going to be something in R3, because there are 3 variables, is going to be 0, 1, 0, and 1, 0, -1, corresponding to the 2 free variables x2 and x3 in my matrix. And if we think about this graphically, we have that null space of A is going to be a subspace of R3. And since it is 2 vectors, then this is going to be a plane in R3. This is what we talked about in the previous section, visualizing subspaces in R3. If we think about the row space of A, it's going to be all of the non-zero rows of A, and we can represent them as column vectors if we want. So the non-zero row here is 1, 0, 1. We're representing it as a column vector, and therefore row of A is a line in R3. It's a subspace of R3, and it is a line. The column space of A is going to correspond to the pivots of A, in which there is 1, and look at the corresponding pivot column in the original matrix A, 1, 2, and that means that that's going to be a subspace of R2, and that's going to be a line in R2. And then to look at the null space of A transpose, we can look at A transpose here. That's going to be 1, 0, 1, 2, 0, 2. And if you row reduce this, this will get us down to 1, 0, 0, 2, 0, 0. There's 1 free variable there, and we can get the null space is going to be the span of -2, 1. A basis for that is going to be -2, 1. And therefore, that's going to be a line in R2. And if we think about this visually, these 4 subspaces, we're going to have a picture on the next page. It shows the relationship between what we're talking about here. So if we think about the null space of A and the row space of A, the null space of A was a plane in R3, and the row space of A was a line in R3. And what's true about these is that they are orthogonal, or that they are perpendicular subspaces. That line actually hits that plane at an orthogonal angle, at an angle of 90 degrees, or pi over 2 radians. And in the same way, the subspaces of null space of A transpose and the column space of A, note that the row space of A is equal to the column space of A transpose. They also come together at a 90-degree angle, or the angle between those 2 lines is going to be pi over 2 radians, and those are going to be orthogonal. And that's always true, both of these were lines in R2. Now there is much more to say about the relationships between the null space and the column space and the corresponding spaces of the transpose, that these are orthogonal. There's lots you can do with that. The purpose of this exercise right here is to just show some of these relationships between these important concepts graphically in terms of the subspaces, looking ahead to future topics beyond the scope of this course. So let's look at one more example, and then we're going to talk about the invertible matrix theorem. The rank theorem provides us with a powerful tool for determining information about a system of equations. And if we look back to the first chapter of this course, we talked about solving systems of equations, and one of the first questions we asked was, is the system consistent? Does it have a unique solution? And does it have infinitely many solutions if they are consistent? Or is there no solution to that system of equations? So now let's look at a kind of generic example where we have a scientist solves a homogeneous system. That's going to be AX equals 0 of 50 equations in 54 variables. So what that means is that the matrix A is going to be a 50 by 54 matrix. The matrix, or the vector X, is going to be a 54 by 1. That's going to be something in R54. And this 0 vector is going to be something in, that's a 50 by 1 0 vector, or something in R50. So that system of equations is solved and finds that exactly 4 of the unknowns are free variables. Can the scientist be certain that any associated non-homogeneous system, that is, looking at AX equals B for any B in R50, will that have a solution? So we may know something about the solution of AX equals 0. Can we be certain about the solution of AX equals B? So, looking at what we did in this section, we know that the rank of A is equal to the dimension of the column space of A. That's going to be the number of pivot columns of A. And the nullity of A, which is equal to the dimension of the null space, is equal to the number of free variables. And in this case, we have A is a 54 by 50 matrix, and by the rank theorem, or the rank nullity theorem, we know that the rank of A plus the nullity of A is equal to n. N in this case is 54. And the null space of A is 4. That is the number of free variables, which we are given in the problem, is 4. This means that the rank of A is 50. And if we think about our matrix A, since it's a 50 by 54 matrix, we know that there is going to be a pivot in every row, as there has to be 50 pivots. 50 pivot columns, 50 pivots. There are 50 pivots. So because there's a pivot in every row, we talked about in the first chapter that if there's a pivot in every row, this means that there is a solution to every non-homogeneous system AX equals B. So just with some information about the number of free variables, we can say something about the existence of solutions for any non-homogeneous system. And then finally, we can wrap up this course by talking about the invertible matrix theorem. All of these things are going to be equivalent to A being invertible. And there are a lot of others that we discussed in previous sections, and now we have 6 more that we can add to it. So what is equivalent to A being invertible, A inverse existing? We know that the columns of A could form a basis for Rn. That means that there is a pivot in every column. Every column is a pivot column. We know that this can mean that the column space of A is just equal to Rn, that it spans all of Rn. This is also true that the dimension of the column space, which is equal to the rank of A, is equal to n. This is also true that the null space is equal to just the 0 vector, or that the null space, the dimension of the null space, the nullity is A, or is 0. All of those things say the same thing. So to be invertible, we're saying that there are no free variables, so the nullity is 0, and that there's a pivot in every column, which means that the column space of A is as large as we can make it, in this case n. And we have that the rank of A plus the nullity of A is equal to n. So if we go back through the entire invertible matrix theorem, it's a nice bow on this entire semester that we can see the relationship between a lot of different things that we've talked about in this course. We've also gone back just in this section alone to so many ideas in Chapter 1, and a lot of those can be brought back in Chapter 2 and Chapter 3 and the other chapters that we've gone over. And a lot of these ideas are similar, and there's lots of ways to get to an answer thinking about different properties of the matrix, all of them coming from the row-reduced echelon form of the matrix.